Hello everyone. This video will be the 11.5 problem session. If I can get it to work, let's see. There we go. So recall that 11.5 is alternating series test. So let's try and test some of these alternating series for convergence or divergence. All right. How about this series? So what clues me in that I should use alternating series test, at least try alternating series test, is this alternating term. Okay, so I see this. This is going to change the sign of my terms. Let's see, the odd terms will be negative and the even terms will be positive. So I have an alternating series. So let's try and use alternating series test to see if this converges. So recall what I need for my alternating series test. I need to check my conditions, right? And what are my conditions? I need an plus 1 less than or equal to an, and I need limit of an going to or equal to 0 as n goes to infinity. Okay, so what do I mean here by these the an plus 1s and this an? I mean the numerical part of my terms of my series. So I ignore the sign change, or if you want to think about it this way, it's kind of like taking the absolute value of this. If I take the absolute value of these terms, the negative 1 to the power n disappears, and I'm just left with e to the negative n. Okay, so what's bigger, e to the negative n plus 1 or e to the negative n? Well, remember what this e to the negative n is. Let's see, e to the negative n would be 1 over e to the n, right? And e to the negative n plus 1 would be 1 over e to the n plus 1. So let's see, I have these fractions, and look at the denominators. Which is bigger? Let's see, I have e to a larger power over here, so I'm dividing by a larger number on the left side. So I should have this. Okay, so an plus 1 is less than or equal to an. Okay, so that condition is satisfied. Now I need to show, or I need to be certain that the limit of an is 0. Okay, so what is the limit of e to the negative n as n goes to infinity? Well, let's see. Again, we have e to the negative n as 1 over e to the n, right? So as n gets really big, this e to the n gets really big, right? And I'm dividing by a larger and larger number. And that goes on forever. So I should be getting closer and closer to 0. So yeah, this limit should be equal to 0. So, all right, that condition is satisfied as well. So I've got my two conditions satisfied. So what does my alternating series test tell me? As long as these two conditions are satisfied, let's call them A and B, boom, my series is going to be convergent. Okay, so now step 2, let's just kind of conclude. I say by alternating series test, series is convergent. Okay, so it's pretty straightforward. It's maybe even easier to apply than something like the integral test. In the integral test, when we were checking our conditions, maybe a couple of them were easy, and then to show the terms of my sequence were decreasing, or my function was decreasing, I would have to find the derivative, right, and show the derivative was less than or equal to 0. So there was a little bit of work involved in the confirming the steps, but in this, confirming these conditions are pretty easy. And then the next step is just making my conclusion. Okay, so pretty straightforward. So that's all for this problem. Okay, let's check another problem. This one might look a little weird. Okay, so now we have an alternating series, -1 to the power n minus 1, and then we have arctan, or tan inverse of n. So the alternating sign tells me I should try and use alternating series test. So step 1 would be checking my conditions. Okay, so let's see, what are my conditions? I need an plus 1 less than or equal to an. All right, is this the case? Think about arctan. Maybe it'd be hard to set up as an inequality, but think about the graph of arctan. What does the graph of arctan look like? If I'm not mistaken, graph of arctan looks like this, right? So this graph is actually, let's see, this function is actually increasing, right? Let's say n is here and n plus 1 is here. Okay, so arctan is getting bigger as n gets bigger. So I should actually have the opposite inequality. I shouldn't have this. I should have an plus 1 is greater than or equal to an. And on the uh, same tack, is the limit of this function equal to 0? No, as it, let's see, it goes to pi over 2, I believe. So as n goes towards infinity, our function gets closer and closer to pi over 2. So the limit of an does not equal 0 either. So neither condition is met. But what's really important, how we can make our conclusion, is actually by this condition here. So we have the limit of the terms inside the series is not equal to 0. So what does that tell us? It tells us our series is divergent. But how do we say it's divergent? We do not say it's divergent by alternating series test. Remember, we never say that. We say it's divergent by divergence test. And if we want to be specific, we could say because limit of an equals pi over 2. All right. So let's try a couple more problems. So some of these series with trig stuff are actually alternating series, even though they might not look like it. Let's try some of these tricky looking ones. And let's actually start our series at n equals 0. Okay, so this is our series, and at first it doesn't seem like an alternating series, right? Because there's no -1 to the power n term. But think about what's happening with uh, sine of this, sine of n plus 1/2 times pi. Okay, when n equals 0, what do I have? I have sine of pi over 2, which is equal to 1. What about when n equals, so let's keep track of what's going on. We got n equals 0 here, n equals 1. Okay. What do I have? I have sine of 3 pi over 2, which is -1. And then maybe you can see the pattern already. If I have n equals 2, I would have sine 5 pi over 2, which is equal to 1. and n equals 3. Okay, we're going to get -1, +1, and so on. So the alternating sign is actually coming from my trig function here. Okay, so this is an alternating series, and if I want to make that clear, I could say that this series is equal to this series. And let's see, first term would be positive. Okay, so it would be this. Okay, so I could rewrite this series like this. So if I plug in 0, okay, I would get -1 to the power 0, which is 1, which would make my first term positive, which matches with what I have originally. Okay, so now that it's clear that this is an alternating series, let's try our alternating series test. Okay, I need to check my conditions. Is an plus 1 less than or equal to an? Again, I'm going to ignore the alternating sign now. So I want to say, is 1 over 1 plus square root of n plus 1, is that less than or equal to this? And yeah, again, I'm dividing by a larger number on the left. Okay, so that holds. Okay, so my first condition holds. And is limit of an, as n goes to infinity, is that equal to 0? Well, again, let's see. I could focus on this 1 over 1 plus square root of n. What happens as n gets really big, dividing by a bigger and bigger number. So that should be going to 0. Okay. So my conditions are met. So that's all I need to check for alternating series. So I can say series convergent by alternating series test. All right, let's try another one of these trig ones. How about this? Okay, so again, let's check what's going on. At n equals 1, I have, let's see, this would be cosine of 1 pi. Cosine of 1 pi is -1, right? So I'd have, let's see, I'd have -n over 2 to the n. At n equals 2, cosine of 2 pi would be 1, and I'd have n over 2 to the n. Let's see, and let's be specific. If n equals 1, I would have 1 over 2. If n equals 2, I'd have 2 over 4. N equals 3. Okay, again, I'd be back to -1, so I'd have -3 over 8, and so on. So I can see that this series should be equivalent to this. So I have an alternating series. Okay, here's my alternating term. And then my numerical term is n over 2 to the power n. Okay, so now I need to check my conditions. Is an plus 1 less than or equal to an? So this might be a little, excuse me. So this condition is, let's see, this will probably be the most difficult case of confirming this first step that we've had. Let's see, what are the numerical terms as we go through? The first one gives us 1/2, and the second one, okay, we have 2 over 4, which is equal to. Okay, so we don't have less than or equal to, we have equal to at first. And then let's see, the next one, numerical term is going to be 3 over 8, right? And then the next one will be, okay, 4 over 16. Okay. So these first two are equal, and then, okay, this one's, the third one's less than or equal to the second one. Fourth one's less than or equal to the third one. Okay, now maybe we can see a pattern that it's decreasing. That's really if we can kind of get the sense that that's going to be the case, that's fine. Another way to argue this is, remember the hierarchy of functions that I showed you guys in class? Let's see, how does n, the function n, compare to the function 2 to the n? Or if we're thinking about functions of x, how does the function x compare to the function 2 to the x, or even, you know, just some general number b to the x? If b is greater than or equal to 1, we wrote it like this, that this function is going to be much less than or equal to, much less than this function. What does this double less than mean? It means we're talking about the rate of increase, meaning this function increases a lot faster than this function. So if I had a fraction like this, okay, this fraction is going to go to 0 because this denominator is increasing so much faster than this function on top. So eventually, this will be this b to the x, no matter what b is, as long as b is greater than 1, eventually this is going to get way bigger than this function x. Okay, so eventually, yes, this this b to the x will be much bigger than x, and that means if I have a little increase in x down here, that's going to outweigh the increase in x up here. So that's a kind of long roundabout way of saying that if I have this condition in my hierarchy of functions, my function, if I and then I turn it into a fraction, my fraction should be decreasing. Okay, so if I have something like this, n over 2 to the n, and I know, okay, n is not that. So if I have a fraction like this, and I know from my hierarchy of functions n is to the left of 2 to the n, I know that eventually an plus 1 is going to be less than or equal to an. Okay. If that's too complicated, just write out several terms and confirm that this does hold, that eventually our terms are decreasing. Okay, let's see. What is next? What is my next condition? I need to show that the limit is going to 0. And again, that holds from this hierarchy of functions. Okay, if erase all this. Well, that's good enough. Okay, so that holds from this hierarchy of functions. I need to show that the limit of n over 2 to the n is 0. And since n is to the left of 2 to the n in this hierarchy of functions, I know that is going to be the case. Okay, so both conditions hold. So this should be convergent, and it's going to be convergent by alternating series test. And let's see, let's revisit that for a second. Another way to think about how to show these conditions, these two conditions, is turn my terms. Let's see, I have n over 2 to the n. Let's actually go to a new page. Let's talk about different ways to show this. What do I want to show? I want to show an plus 1 is less than or equal to an, and I want to show limit an goes to 0. I could turn this into a function of x, right? Okay, and consider this function now. And now if I wanted to show, let's see, if I wanted to show this function, oh, this should be an x as well. So this is a function, right? And if I wanted to show this function's decreasing, I would show the derivative is negative. Okay, so let's think about what the derivative of this is. Let's see, product rule or quotient rule, however you want to attack this. Let's see, I'll rewrite this as x times 2 to the negative x, and I'll do product rule. Okay, so what's the derivative of this? It'd be 2 to the negative x, right, plus the derivative of 2 to the negative x. Well, what's the derivative of 2 to the negative x? Let's go up here for a second. I could rewrite 2 to the negative x as e to the negative x ln of 2, which might seem weird to do, but now I know how to find derivatives of e to the powers of whatever, right? The derivative of this would be negative ln of 2 e negative x ln of 2, which equals negative ln of 2 to the negative x. Okay. Let's see. So my derivative here is 2 to the negative x, 1 minus ln of 2. And I just realized I'm missing an x. There should be an x there, and so there should be an x there. Okay. So we're considering the interval 1 to infinity, right? So on the interval 1 to infinity, what's bigger, 1 or this? Let's see. It should be, let's see. Well, at first, 1 is bigger, right? Let's see. ln of 2 is a bit less than 1. It's like 0.9 something, perhaps. And let's see, I'm multiplying it by 1, so that doesn't change anything. So at first, 1 is bigger. Okay, so at first, derivatives are positive. But then what happens when I go to x equals 2? Okay, then this term would be a bit bigger. And then from then on, my derivative will be negative. So this function is decreasing. It's decreasing on 2 to infinity. So that means my series is decreasing on my series is decreasing on 2 to infinity, and that's good enough. As long as it's decreasing eventually, we can use the alternating series test, okay? So this condition holds on this interval, okay? So that's good enough. So boom, that condition holds. And then again, how could we show that this limit equals 0? Well, we could try L'Hopital's rule, right? Okay, so L'Hopital's rule would give us this. Okay, and what's the limit of this? The limit of this would be 0. Okay, so my limit of my terms is 0 as well. So that's a bit more methodical way to show these conditions hold. All right, let's try another trig problem. All right, now it's clear that this is an alternating series, so the alternating term isn't coming from the trig stuff, but we're still having to deal with these cosines. Okay, so first step is to check my conditions. Okay, is an plus 1 less than or equal to an? Okay, so consider what's happening with cosine as, let's see, we have pi over n. Okay, so let's think about the graph of cosine. Okay, so at n equals 1, we're here, right? We're at cosine of pi equals -1. Okay. Is this the best way to show that? No. Let's see. Let's see. So this, okay, here's a better way to think about this. At cosine. Okay, so this would be cosine of 0, right? We're at 1. This would be pi over 2, and then my graph goes like this. Okay. How about this? So at pi, our graph is here. We're at -1. And then what happens as n gets bigger? As n gets bigger, let's see, cosine pi over 2 would be there, okay? So we'd be at 0. Okay, so we're going from -1 to 0. And then as n gets bigger, we move this direction along our graph, right? We move towards 0. As n gets bigger, this term's going to 0. So cosine, my values of cosine should be getting closer and closer to this, which is 1. But it's never going to go beyond that, right? We're always going to be stuck on this part of the graph. So my function's actually increasing, right? I started at -1 and I'm increasing towards +1. So this condition doesn't hold. Okay. And is that so this by itself isn't enough to say my series is divergent, right? Remember what I said in the lecture video. If this condition fails, we know nothing. But let's now try and apply this logic to the second condition. Okay, is limit an equal to 0? Okay, no, we said limit a, as n increases, we're getting closer and closer to 1, right? So the limit of an is equal to 1. Okay, so now what do we say? We say our series is divergent by divergence test. Okay, so this series is divergent, and we say it's divergent by the divergence test. All right, one last example, guys. And this example, we're going to go back to the hierarchy of functions. So let's consider this. So this one's tricky in that, okay, let's see. It's clear it's an alternating series from this term. And then let's see what's going on with the terms. Okay, if n equals 1, we'd have 1 over 1. If n equals 2, we'd have, let's see, 2 squared, we'd have 4 over 2. Okay, so it's increasing at first. N equals 3. Is it always going to be increasing? Let's see. We'd have 3 to the power 3. We'd have 27 over 6. Okay, is that increasing? Let's see. This is a bit bigger than 4. Yeah, so it's increasing. Okay, so maybe it's clear from the start that it's increasing. Okay, so condition 1 fails. And let's see, how about one more term, 4 to the 4. That's what? 4 squared would be 16, 3 would be like 256, I think. Okay, so 256, so this is maybe a bit more than 10. Okay, let's see. So we'll call this about 4-ish, call this about 10-ish. This is equal to 2. Okay. So, all right. So it's clear from the start that it's increasing. Is it always going to be increasing? That is harder to determine, right? But again, if we go to our hierarchy of functions, if you recall that, you can find this on the internet just by looking up hierarchy of functions. You'll find it somewhere. We have n factorial is increasing slower than n to the power n. Okay. So what does that mean in terms of our fraction? Okay, so this thing on the top is growing a lot faster than this thing on the bottom. So that means my function should be getting bigger and bigger all the time, past a certain point at least. And it looks like it's true from the start. Okay, so my function, my terms should be increasing. Okay, so I wanted this, but I don't have that. In fact, it looks like the opposite. It looks like right from the start, my terms are increasing. Okay. And let's see, what does that mean for condition 2? Okay, so I'm checking my conditions. Okay, so condition 1 fails. What's the limit of an? Again, from this hierarchy of functions, when I think about my graph, this stuff, or excuse me, my fraction, this stuff on top is increasing a lot faster than the stuff on the bottom. So my fraction should be going up to infinity. My limit should be going to infinity. Okay, so this condition fails. So my series is not going to be divergent. It's not going to be convergent. It's going to be divergent. And it's going to be divergent. Why? By divergence test, because the limit does not equal 0. The limit of the terms does not equal 0. Okay. So why did we have to use this hierarchy of functions? We couldn't use the techniques we used on the previous one. We couldn't turn this into a function and use things like L'Hopital's or anything like that, because we can't turn factorial into a function, right? Factorial is only defined for integers, okay? So we can't do x factorial if x is like 1.4, okay? Factorial only works for integers, okay? There is a function version of factorial called the gamma function, but that's a whole other kettle of fish, and we don't want to think about that. Really, I would say there's no good way to turn n factorial into a function of x, okay, without introducing a lot of other stuff. Okay, so when you see factorial, maybe think hierarchy of functions, okay? All right, so I think that's a good number of examples. We covered some convergent stuff and we covered some divergent stuff. Hopefully you guys see how to apply this alternating series test. Let me know if you have any questions. All right, good luck.